In this video, I'm going to give some intuition about where the information comes from in order to draw causal inferences in the direction of causation twin model. Let's consider two different states of reality. Let's consider the figure on the left-hand side of the slide first. This model shows a pair of twins, twin 1 on the left and twin 2 on the right, who have been measured on two observed variables. Variable A, indicated by the boxes at the top of the diagram, and variable B, denoted by boxes at the bottom of the diagram. The observed variables are influenced by latent factors due to additive genetics A, dominance genetics D, the common environment C, and the unique environment E. And these latent variables are correlated between MZ and DC twins by the usual values given by biometrical genetics theory. We assume that all the latent variables in this diagram have variance 1. Note that in this example, trait A and trait B are influenced by quite different sources of variation. Trait A is caused by common environmental factors and the unique environment. In contrast, trait B is caused by additive genetic factors, dominance genetic factors, and the unique environment. I've deliberately chosen this unusual situation to facilitate explication of the model, as we'll see in a moment. However, it's worth noting that the statistical power to resolve the different directions of causation using these models is greatest when the etiology of trait A and the etiology of trait B are very different. Finally, the unidirectional arrow from trait A to trait B indicates that under this model, variable A is causal for variable B. The information to distinguish the different directions of causation in this model comes from the cross-twin, cross-trait covariances. What do I mean by cross-twin, cross-trait covariance? I mean, for example, the covariance between twin 1 variable A and twin 2 variable B, or equivalently, the covariance between twin 1 variable B and twin 2 variable A. Let's take a moment now to calculate the expected cross-twin, cross-trait covariance between MZ pairs and between DZ twin pairs under this model for causation. If you're not familiar with the rules for path analysis, check out the video by Matt Keller at the link below about this topic. He could certainly do with the views. In order to calculate the expected cross-twin, cross-trait covariance between MZ pairs, we start at twin 1 variable B and trace backwards all the way to twin 2 variable A. Let's do that now. We start at twin 1 variable B, trace backwards along the arrow to twin 1 variable A, backwards again along the arrow to variable C, then round the two-headed arrow, changing direction and then tracing forwards through the latent variable C, forward through the C subscript A path to twin 2 variable A. Remembering that the contribution of a chain of paths to the overall covariance is given by the product of the path coefficients, putting this all together gives IB times CA times 1 times CA, or CA squared times IB. Note that this is the only valid path from twin 1 variable B to twin 2 variable A. If we had tried tracing backwards from twin 1 variable B through the latent variable A and across to the other twin, we would run into opposing arrowheads on the other side of the diagram. Thus, it's not possible to get from twin 1 variable B to twin 2 variable A by this path. Same deal with tracing back along the paths involving D. Finally, note that we have calculated the expected covariance between twin 1 variable B and twin 2 variable A. It would also have been possible to calculate the expected covariance between twin 1 variable A and twin 2 variable B. If we'd done this, we would have obtained the exact same covariance. Pause the video now and try it yourself. So we have our expected cross-twin cross-trait covariance as CA squared times IB, assuming that variable A causes variable B. Notice that the expected cross-twin cross-trait covariance doesn't change according to whether you are an MZ or a DZ twin. That fact will be important in a moment when it comes to distinguishing the direction of causation. So what happens when variable B causes variable A? Let's consider the direction of causation model on the right half of the slide. Here the model is exactly the same, only the direction of causation is in the opposite direction, with variable B causing variable A. Let's calculate the expected cross-twin cross-trait covariances. We start at twin 1 variable B and trace backwards through the latent variable A, through the two-headed arrow, changing direction from backwards to forwards, through the latent A variable, forward along the A path, through twin 2 variable B, along the causal path from variable B, and finally to twin 2 variable A. The covariance explained by this path is AB times 1 for MZ twins, or 0.5 for DZ twins, times AB times IA. Putting that all together yields IA times AB squared for MZ twins, and 1/2 IA times AB squared for DZ twins. But this is not the only path that is possible from twin 1 variable B to twin 2 variable A. Starting at variable B, we can also go backwards along the path for dominance, through the latent dominance variable, around the two-headed arrow and changing directions from backwards to forwards, through the latent dominance variable, forward through the dominance path, through twin 2 variable B, forward through the causal path from variable B to variable A, total contribution from this path is given by IA times DB squared for MZ twins and 1/4 times IA times DB squared for DZ twins. Adding the contributions through the A and D paths gives the expected covariance for MZ and DZ twins. Note that we could have got exactly the same answer for the expected cross-twin cross-trait covariance if we had started at twin 1 variable A and traced a path to twin 1 variable B. Pause the video and take a few minutes to do that now. Finally, note that you can't get from twin 2 variable A to twin 1 variable B by going through the C paths because of the opposing arrowheads. So this slide shows the expected cross-twin cross-trait covariances under both causal directions. Under the model, where variable A causes variable B, the cross-twin cross-trait covariance is the same in MZ and DZ twins. Under the model where variable B causes variable A, the expected cross-twin cross-trait covariance differs between MZ and DZ twins. That's a long way of saying that the pattern of cross-twin cross-trait covariances provides information as to the direction of causation between variables A and B. And so that is where the information is coming from to distinguish between the different models. In the next video, I'm going to talk about some of the problems with the twin direction of causation model.